Hello. Today, as you can see, we're going to have a demo for the most over-architected worst chat app ever. And we're going to do this in a couple phases. The first one is we're just going to look at how the chat works, like it is a chat app, sort of like Slack or one of those other very popular apps. And even the demo apps that you'll see elsewhere. But for us, it's just a crappy chat app. I mean, there's no other real good way to put it. It's going to be good for a laugh. And then we're going to go to a deep dive of what's actually happening behind the scenes for anyone who wants more than a laugh or wants to see how a DLT can actually scale through the simplicity of the protocol. We're going to talk about how really what we're doing behind the scenes. And then maybe we'll do some where to go from there. But let's just see the crappy chat app, and then we'll see if you want to hang around. So first, as you can see, we have several windows open here. Here is the horrifically viewed, ignoring the dark of the Android, the dark view. And then here is the simulator for the iPhone. And then over here, this is Chrome. As you can see, right here is Chrome, a Chrome extension. And then here is a Chrome web app being hosted with an Angular dev server. And then here's the same thing on Firefox. So here's the web app. The puppy's playing with the kitty. This is what we did last video, if you're looking at this temporally. We're going to go into the demo here. And then here's the same thing as a Mozilla extension. And that's using the web ext. But so anyway, we have 6 different clients. They're going to be talking, hopefully. And we're just going to do very, very basic stuff here. So starting here in the extension. First, I want to point out you have the little stars here and little rocket ship. These stars, this is kind of like what you think of as the cloud right now. But the cloud is a centralized concept, and spaces are how we're going to view the decentralized aspect of this. So right now, most of the world thinks in terms of nodes. They think of mesh nodes. That's certainly how I used to think. But this is kind of like thinking of space like we think of as space instead of planets. So it's an interesting concept. But anyway, the dark background means that this is automatically syncing, and that's going to be for another video of how to do a synchronization space for this. It's kind of like Dropbox for our DLT data. But so that's what these little stars here mean. This one's not automatically syncing. We're going to go inside the demo. Now you'll see the stars are dark. There are the stars, the background's dark. That means that they're auto-syncing right now. Okay, so we're in the Mozilla extension, and we're just going to write a little play on words here. So the text, any of the text ibgibs, I arbitrarily call comment, because that's just a use case. It's kind of like growing up like a metonym. So we're just going to hit the little chat. We typed in our initial comment. Here's the horrifically slow, I'm not an artist, front-end person at all, loading animation. And it's even slower right now. The Mozilla extension's a little slower, but obviously I have 6 of these things going, including the streaming software, so it's going to be a little bit even slower to make it even crappier of a chat app. But we see initial comment here. It's got a timestamp. So that's like, oh, fun. We have a chat app. We've added something. It has not shown up anywhere else, even though they're running on my local machine. That's because right now the synchronization space that it uses is using what's called long polling. So there's no WebSockets. I had a previous implementation that's using WebSockets, but it was centralized using a central server. This is completely decentralized. It can use WebSockets if we create a WebSocket adapter, but right now we have an adapter that lives as an AWS implementation. So, and that's the only one we have right now. We'll go over that in another video. The important part is that it's very slow and it uses long polling. So if we just sat here, eventually this rocket here is gonna start spinning, but I'll probably just go ahead and hit the button. So what that does is it pushes to the synchronization space. So right now our terrible chat app is talking to the interwebs. So we'll see how long that takes here. I'm also terrible at YouTube and editing, so maybe I'll edit this out, maybe I won't. I don't know. While we're doing that, we'll try going over here and push our luck for a demo. All right, so this, because it's an occasionally connected design, so this, you can think of each of these as being kind of like a local GitHub repository. And what they're doing is they're going to be pushing to a remote that's implemented via AWS, which is using DynamoDB and S3. So that finally finished. So what this is actually going to do is, I just pushed it, otherwise we'll see, oh, see here, there's a little badge saying that it saw, if you can see my mouse there, a little badge that says, oh, I found an update with the rocket. Here, this one says it also. We'll go back over to Firefox. This one says it also. This one didn't because we hit the little rocket. So we've already updated over here. And then here it says it also. So we'll see what happens when we hit these. What the hell, we'll do it at the same time. I'll save this one. So each of these was blank first when we started syncing. Oh, see there? That one has now synced. This one has now synced. It's reloading the new data. This one's reloading the new data. This one's a little bit different, and we'll go into that, how this is different. But just notice it has the initial comment. So this one and this, the iOS, these two had two different modifications. So if you think of in Git, that sort of thing, when you have two timelines, two branches that make simultaneous modifications. It's a little bit different when you go to merge them because it's not just a fast forward merge. You know, it's slightly different. And we'll go into the innards of that. But for right now, we're just looking and admiring the glory of how euphemistically crappy this our chat app is. Oh, look, we got some action over here on the Android. So while that's going on, we'll go over here. This is the Chrome web side of it, and we'll see what happens if we hit the little camera button here. Oh, there we go. Didn't want to give us a fake camera. Maybe Firefox wants to give us a fake camera. Nope. I know I can't do it on there. Let's see the fake camera on Android. Here we go. This one's got it. Alright, so now this is their interesting little 3D camera. Oh, we'll take a picture of the kitty here. Sure. So that's going. We could move off of this, go somewhere else while that's going. Oh yeah, feel the speed. Well, I better hit the brakes. I'm going too fast here. I don't really think the CSS is slowing it down any. It's mostly what it has to do. My poor Angular skills. Anyway, so we moved off while this was happening here. Here's the cat. Do we want to wait for it to automatic? No, we'll just go ahead and push it. I'm lazy, or impatient, I should say. So now we've added a camera picture locally on the Android device. The data is actually stored as JSON files locally on the device. And then now when it's synchronizing, it's pushing to the DynamoDB and S3 bucket. It's actually using S3 bucket for pictures. Little implementation detail. Linking the DynamoDB with the S3, since these are already content addressed, meaning they're addressed by the hash of the data. You already have a convenient indexing mechanism between DynamoDB and S3, but that's deep in the weeds. Boy, it's evens. Wow. Can't overestimate how long it's going to take in a demo with my computer at 100 degrees Celsius. Boy, somebody out there wants to edit. It's going to be great. So sweetie. Okay, hold on a second. The puppy dog wants food. You You don't get fed for another 30 minutes. What are you doing? Okay. Meanwhile, I'll try in small ones. There we go. So the local files are just they're JSON files. They're stored locally on the machine. Nope, no, sweetie. And interestingly, in the browsers, they're stored in IndexedDB. So, see here, we already have a little badge. Later on, we'll have it to where you can set it to auto synchronize. But for right now, we have a little badge indicator to let us know how many, at a minimum, how many new instances of March 27 demo does it have. We'll go over here. Now, at the same time, this one is pushing to the synchronization space, and then these are pulling. So your guess is as good as mine on whether or not it's going to show. Okay, so this one just showed the Android because this hasn't finished. This also showing the Android. And the Firefox Extension. Has, ta-da, the Android. All right, so our terrible, terrible chat app. Unsurprisingly, since this hasn't finished, has synchronized over all the different spaces. So this is the Mozilla extension that's using IndexedDB only for that Mozilla extension. This one is using the Firefox profile. I believe Chrome also has a profile, and then it also has an extension space. So, but those are using the IndexedDB. It's actually using the ionic storage, which is has an IndexedDB, and then it falls back to maybe local storage. But since that has a very low limit, it's next to worthless. But the interesting thing here is that when thinking about decentralized things, I know there are other DLT dapp architectures which they have their pluses and minuses. One is they have huge investments, but I just disagree with some of how they approach it. Whereas this is a very, very thin layer, a thin protocol on top of it. It's meant to be equivalent to more like how the original HTTP was designed. probably isn't going to go. So anyway, so that is a terrible, terrible chat app, right? Very awful. So, but what we'll do is we'll kill some of these to free up some space. Right. We'll keep these open. And then I'm going to walk you through some of the code. Manifest background, that's for the also, before we understand this, we do need to look to see just a little bit about the protocol itself. Right. So here we're at March 27 demo, right? This is what it looks like. Maybe you think of this as like the chat room or the channel or whatever paradigm that you're used to thinking of. But really, this is just, right now, it is an ibgib, or ibgib, or however you want to pronounce it. It's G like in gauge. So if we look at this one that we're in comment March 27 DEM. Okay, this is our context. That's what I call the context. This is kind of like looking at the ibgib as a folder. So instead of thinking of things as being something, one of the ways to move away from the old way of thinking of files and folders and moving beyond that is to start thinking of something and then your view into something. So in this case, this is an ibgib being used as a folder, or like, you know, in the sense that it is a container or has relationships to other things, whether they're folders or files. If you know anything about the internals of Git, it's kind of like acting like the tree, only it's not just the tree. Ultimately, it's the same shape. Every ibgib has the same shape. That's what I'm talking about, the thin layer. And it's all about how to connect things with data and metadata such that the metadata lives alongside the data. So like, as opposed to say Git internally has a Git object DLT. It actually has a Merkle graph inside of it that it uses for Git objects. But the configuration for your repository is like your base thing, right? Nothing can go beneath it, and it's a special thing. Whereas this, any one of these ibgibs can be a repository. Each one of them is a timeline. And so each one has 4 fields. It has the ib and the gib. The ib and the gib, they're purposefully, it's a neologism because we don't really have anything like it right now. But so the ib is mostly for metadata that you want in the address. Okay. So in this case, the schema I use, the very simple schema that I use for comments is first there's a comment atom, or whatever you want to call it, a constant, and then a little bit of the text of the comment, just if you want to see it. Like when I look at it, I go, oh, there's a comment, March 27, that's the one I'm looking at. For a lot of users, completely transparent to this, or completely, ignorant of this. Gib, we'll come back to the gib. Data is for intrinsic relationships, usually to primitives. So it's not pointing to other ibgibs. It's the internal data. It's kind of like what you think of as a file. So it's intrinsic to this local ibgib, this one right here. And then here's the relations. That's all of these. Okay. And those are named relationships to other ibgibs. In graph jargon, they're sometimes thought of as edges or links, but they are named links. And some people would say that this is what makes it a DAG, a directed acyclic graph. And in a sense, it is. But the very, very key thing is each one has a past and an ancestor. Okay? Okay. So, what's so special about a past and ancestor? Well, if you know anything about blockchains, each block has a Merkle-link, a cryptographic link to the previous block. And that's also like the past. So that's a linked list. You have to have one block in order to get to a pointer to another block. One block here, it's got a pointer to the previous one. It creates a forward pointing timeline. One pointer here, each time, each node has a single relationship to the previous one. The past can work either like a blockchain, where in that it can either have just one pointer, or in this case, I have comments incorporate pointers to every point in its history. So it's a trade-off between, depending on your use case, on whether you want to have storage or processing, right? So if you have a linked list, it's going to take longer to traverse the graph, or in that case, the line, but it's going to store less. Whereas this, we're eating storage, we're wasting this, because each ibgib grows, the past grows by 1. So, the next one, when we add a comment, let's start from the beginning. The very first one is right here, and it's temporal junction point. We'll get to what that is. But so, when we added this initial comment, we added this, we had this another initial comment, it went to this, and then we added the picture, and then it went to this. So each one of these is March 27th. It's our context, right? So this is the past of that. Okay, so this is the past of this ibgib's context. And what that does is it creates a stream for an ibgib. If we think of it, in our case, we are doing it as having a stream. But so starting with this, each successive change is a monotonically increasing, append-only log of nodes in the what you think of as a directed acyclic graph. But since it can point to itself, if you're thinking of individual points in time, yes, it's directed and it's acyclic. But it can point to itself. It can say self, comment, blah, blah, blah. In fact, that's what this TJP is very similar to. And all these paths are pointing to its own stream. So in that sense, if you're thinking of streams, it's also cyclic. But anyway, that's a little bit about how the past works. And the main thing is that you have timelines. Okay. Now, the temporal junction point, if you think of in terms of streams, this is like our first instance of this ibgib in existence. So it's the very first one here in the past relationship. Here's the comment, 47, blah, 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 76. It's actually, you can tell it's a little bit shorter than these other ones. TJP, 47, blah, 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 76, right? So that's just the ID for the very first one in time. So this thing, this TJP, and really a unique ID and a timestamp or whatever is what helps make, when you first fork that timeline, it helps it be unique in the universal sense. And so we have a timeline that's every time a mutation happens, which is in this case relating to other comments. We can see right here in the comment relation, remember they're named edges. It has comment, initial comment is the first one, and then comment, also comment over here on iOS. And it also has one relation that's a pick, and that's the Android relationship. We're just going to go back. Tired of seeing that going. It's probably going to go automatically here anyway, because it's going to start polling in a second. But anyway, so that's a little bit about the timelines, okay? Now, the next important thing to know is that, like Git, the timelines are made via sort of like diffs. So even though I didn't design this, saying, oh, how can I be like Git? I came more from the event sourcing world, where you think of events and commands as being an append-only log of domain logic. In this case, the domain logic, the one domain language, has to do with timelines. So we have DNA. So this fork right here is an ibgib living in the graph. Let's see if we'll be lucky here. We're going to duplicate this. And then we're going to paste in the fork, right, that we just looked at. And it's going to load here. It's not going to show anything. But if we look at it, here's our fork. So the fork is an ibgib living on the graph, in the Merkle-linked graph. And here is the information that we used. Temporal junction point, true, true, that's to make it unique. DNA because we want to track DNA. Encounter because we want to have sort of like version numbers And then the type of transform is a fork. But so that's one of the important things is that you want to have this kind of metadata on chain on the graph to where everything ends up being more transferable and more mobile in as simple a way as possible, because you want to be able to start thinking of these things as timelines and projections of timelines. And one more detail on I didn't get back to the gib. So the gib is like what other people have as just the hash, okay? But in ibgib, the gib just happens to be implemented in this case right now as a hash. Sometimes the gib is just a literal gib. But in our case, we have two parts to this gib. First is, this is the hash. It's the hash of the other three fields. It's actually the hash of the hashes concatenated. But so this 55 blah 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 47 is the hash of the ib, and the hash of the data, and the hash of the relations, which are the links. So that's what I call like a punctiliar hash, a hash of one point in time. If you want to think of it as a frame in time or a quantum of time, then you can think of it that way. The second part, this is the gib of the temporal junction point, that thing we were looking at earlier. So 47 blah 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 76 is the TJP, temporal junction point. Remember, that's like our stream ID, only it's not a separate ID. Why have a separate ID when you already have a cryptographic hash? So 47 blah 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 76. So this could be intrinsically validated on if this ibgib is formatted correctly, if the punctiliar hash is the hash of the ib, deterministic hash of the ib, the data, and the relations, and if this temporal junction point is also inside the graph, and that each graph has, valid addresses and that sort of thing. So the addresses here, like this fork, and then caret 9 blah blah blah, that's the ib and gib of this fork ibgib. And so in contrast to many other graphing technologies, what they almost always do, in fact all the ones that I've looked at, they use the hash alone as the address, and then they hard code metadata, when really the whole thing is a metadata address or label that can have some schema. And so you don't have to hard code what the first part is, what the second part is, or if there are three parts or whatever. That's how I went with the ibgib, and this was 10 years ago. Yeah, about 10 years ago. Because you just want the thinnest layer possible without adding extra restrictions, because use cases change. Somebody else may want actually the gib to be the hash to be first, and then additional metadata be second. So you could have the ib be the hash and the gib be the metadata, whatever. And then the interesting thing is that kind of structure, those kinds of decisions can live on chain alongside the data itself, and that is another extremely key part. So right now, what happens is that someone, when they want to make a new software product, they immediately add it to a Git repository. Mine is still in a Git repository because I've had to redo implementation stuff. But anyway, the first thing to do is they add it to Git, and then they create their hard-coded stuff, and then now they have a test net and a main net of other data that lives completely separate. So now the configuration, not only do they have metadata in Git, they have Git metadata living in the Git config folder and stuff like that, where it's not inside the graph. Whereas if you're clever enough about it, you can have the entire thing in a projectable graph, to where you can create homomorphic projections, you can create slices, you can do all sorts of fun things, import space, all sorts of stuff. But the main thing is that you have this one structure that has both data and metadata with as little cryptographic requirements as necessary. Anyway, so that's what the gib is. So each one of these has the ib and the gib, with right now an implicit schema of the ib being first, having a metadata which has its own implicit schema, and the gib having either just the hash or the hash and temporal junction point gib, or down here, if it's just gib, it has no metadata, no cryptographic metadata on top of it. It's what I call a primitive. Okay, and notice there are no types here. So this fork, the ib acts like the type. So that's another difference. What people inevitably do is they go, oh, I have a computer protocol, I immediately want to start enforcing types on top of it. I'm going to have some sort of number type, an integer type, a floating float type, a double, a string type, all these sorts of things. But really, none of that is necessary, just like you can have all sorts of code be checked in to Git, another parallel for Git. But, so anyway, that is the data, and the important part is that we're talking about timelines and merging timelines, similar to when you do a git pull or a git merge. So let's look and see what exactly that looks like. So when we go create the comments, we are working, that's basically like working on our local repo. So local repo change, okay? So that hasn't done anything on our remote, which in our case, in this world, it's the synchronization space. It hasn't done anything to that. It's only local, so that makes it an occasionally connected technology, which I can tell you my previous implementation, one of them, which was written in Elixir, was a centralized one, and I took a bike trip from here. I ended up going from San Antonio to Albuquerque before I ran out of money. But I can tell you, out there where there's no coverage, that it's worthless. It's worthless to have this kind of app, any kind of chat, any kind of collaboration mechanism, because you're not connected, and you can't do anything until you are connected. So in this case, it's an occasionally connected. You see a little one here. It's an occasionally connected scenario. Now that one means that this did automatically push to the remote. I do have that to where that's implemented. But let's go just look at code real briefly. Let's see, how long have we been going here? 45 minutes. Oh, we'll go a little longer here. So we'll look at the action bar. Oh, I can do the screencast mode. That's what it's called. Okay, so when we push that little button, it does right here. Okay, we go to that. Blah, blah, blah. You enter the comment, you the text, blah, blah, blah. These are just UI stuff that, again, I'm terrible at UI. Anyone who is not terrible, in fact, is very good with it. If you're new, you probably don't want to come with me on this, but if you're looking for a challenge, there's many different UIs, and we're architecting this in such a way that you can use any user interface to add items to the chat. In fact, my first implementation, the one that was in Elixir, actually used D3. Used a little force layout. But anyway, so here we're creating the parent primitive, the comment primitive that we're going to fork from. Whenever you create a new ibgib, quote unquote new ibgib, it's actually forking from some existing ibgib, which is going to be some sort of primitive. If it doesn't fork from anything, then we think of it as forking from the root ibgib, which is just ib and gib, or whatever you want to think of it as, or 0, or so we create this, the first gen, we persist it, blah, 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 do some local space stuff. So here's the main thing. All right, so we relate the current ibgib to the new comment address, right, via the comment relationship. So this is locally, this is taking our context ibgib, and it's adding a new relationship to it. So it's mutating the relationships, the extrinsic properties. It's going to get back a result. It's going to have, that result's going to have a new ibgib. So this is all local again. It's going to register the new ibgib, and then it's going to navigate to it. That's the horrific, when you see down here loading. Okay, when you see that loading, that's loading the new local ibgib. So we've just added a couple more. If we look at this, a couple more comments on the comments, and then our pass is going to be a couple more. They're all going to say comment because this is talking about our March 27 comment. But we've added a couple more of these with these last two comments we added. Okay, so that's all local timeline changes stuff. And it stores it in a local space. In fact, when the application boots up, it boots up with a bootstrap like a 0 space, because bootstrapping is a funny thing. And it creates or loads the local space. And then what that does is, now whenever we do something, we're just adding ibgib, either mutating timelines or adding new timelines to our local space. And then that local space, when we go to sync, ibgibs, what that does is that it's going to get the entire dependency graph, and right now it's not optimized, obviously, that's one of the reasons it's very slow, but it gets the entire dependency graph that's locally, that exists locally, okay? It's going to validate it, blah, blah, blah. It's going to get our sync spaces, which we'll do another time on how to create a new sync space. But the important thing is that you have a space, and we'll get into how the ibgib stuff works with spaces and that sort of thing, but which is very important. But for right now, the important thing is that we're looking at is that we get our sync spaces, we go across them. There's all of our sync spaces. We're building up how, what to send there. Then we get all the ibgibs. So there's different things that can happen with local timelines. Like, if you have an object and each object has properties on it, and those properties can change because you have references to them. Remember, each one of those properties, each one of those timelines can itself mutate or change over time. So we've got to get all of our local changes, all the up-to-date stuff, blah, blah, blah. We create a new saga, and then we send that saga to the sync space, which we'll go over here. Here's our dynamo space. Okay, so all right, so here's our space base. We'll go ahead and just look real quick. Because I guess it's hard to get around it. The witness, so we're just walking up the interface, the class hierarchy, I mean. So here's our witness, and here's our basic witness interface, okay? And all it does is it has one function on it, okay? So an ibgib is just data, right? You have the nodes in a graph that's just data. Whereas once you're running, now you have these things that can have behavior. So how do we codify what that behavior is? The way that works is right now is that people have classes or functions that live on a Git repository on their Merkle graph that lives outside of their data. And then we have funky ways of trying to enforce certain versioning for that data. So we have, versioning like both the versioning in the repo itself. We have the now DevOps and CI, CD, different pipelines that we use to try to get those things as similar as possible. But we have that in the ibgib protocol. We have that at the very base level. The whole thing is meant to be timelines mutating. So we don't have the out-of-band difficulties that come with the complexities with that. We try to encapsulate that at the data layer to where even our behavior, so you can think of a witness as being a function that just has one thing, go. Okay, it takes in an arg, which is an ibgib, some data, some memoized reified data, and you get out a memoized reified data, and both your argument and your result are ibgib records. So on chain, you can have the functions themselves. In the future, we'll have, once we have version control implemented, we'll have the functions themselves. We'll have the arguments that they take in and the results of those arguments that come out. And so now we streamline the process Basically, very much like a functional way of looking at composability, where functions and functions and functions. Only in this case, we're calling the function an ibgib, and when it does, when it has behavior, we're calling it a witness. Okay, and that is because we're anthropomorphizing this very purposely. Because in the future, right now we think of a witness protocol or consensus protocol, but really any functions that are happening are a simplest form of a witness protocol. A function is witnessing an argument, and then it's creating a third thing. Okay, so basically we have one outlet for our function to receive arguments, so we can hook into, this is what other languages do locally, right, for what you think of as programming. But we're thinking of this as programming across an infinite space and using a very special way of content addressing to where all of our objects have an address in an infinite space, and now we're talking about taking spaces, sending them to other spaces, transforming them to other spaces, and that sort of thing. So it sounds maybe like it's more complex, but really it's simplifying the entire process of data evolution, and it's looking at it through a more biological lens. So we'll go back to the dynamo space, right? So it's a space base. This architecture just has a bunch of plumbing for, our equivalent of having different types of function signatures is having different argument shapes, which is encapsulated via all this generic stuff here in the TypeScript world that just helps us compile stuff. So anyway, let's get back to the AWS space here. So one of the things is when it receives one of those arguments, when we do the start sync, we have our local space, we create our start arg because we're going to do a sync, there's some modifiers, and we're going to send this to there it is. So we're going to send this to the synchronization space, which is over here, and it needs to route that argument. So with a space, the main thing is it's like a bucket. You can put stuff in. You can, because it's monotonically increasing and append only, you want to be real careful with deletes, but you can put stuff in, and that's the main thing. They don't override each other because it's content addressed. There are collisions in addressing, which is another important reason to have not only the hash be the address, but also the ib part, which is metadata, because that reduces the collisions in a big enough world where you have very, very few edge cases. But so we route and do the command. There's a bunch of plumbing in the bottom that already does routing for a put and a get. But the thing that's special on this one is that it can do a synchronization. So if it's a put, and we're also has a command modifier of sync, then we're going to handle it specially in this class. So we're going to go to that. Otherwise, it's going to do just normal space stuff, puts and gets. Okay, so here's a bunch of overwhelming crap. By the way, I use a lot of vertical space with TypeScript. As you can see, well, the arg is hiding it that I'm setting as an object. But like this, for instance. So some of these files are pretty long. I would, if it were not just me on the team, me and just one other person for higher level stuff, but me doing the coding. Normally I don't have like that, probably a refactor. Normally I'd break it up more, but you know, it's a prototype, getting it implemented. The main thing is I want to try to get people to understand the slightly different paradigm than existing blockchain and DLT approaches. Because I've been working on this since before Bitcoin was a thing. Although the DLT side did coincide about when Bitcoin was around, was coming out. Anyway, so the synchronization, first, this is watches, this is for the notifications, initialization stuff. First, we want to just start off a saga, because this is a long-running saga. And then we're going to immediately return that saga with let's see here, where is it? Oh, when we created the incoming argument has an observable on it. There we go. So this is outside, because it's on the ibgib, not in the data. This is not stored. This is not stored in a space if you're saving the metadata. This is just living in memory at runtime. And the sync info stuff has this observable. Okay, so when we sync, we're sending our local space is sending to our local client proxy, hey, start syncing these ibgibs, this dependency graph. Remember, because we're going to start thinking of graphs of timelines. So we take these graphs of timelines, we say, hey, store this in your synchronization space, which is not just a simple storing, but it's where the most complex stuff happens. And so our local client is going to take your incoming arg, and it's going to use this observable to give you updates, and it's going to immediately return to you, okay, I've got it, I've started on it, I'll update you via, I'm hitting Control minus for the back. Okay, so that's what the ibgib start does. And then here's where the meat of it is. And this is really what I wanted to get to. Spin off to complete sync. Okay, so here, as you can note from all the comments, this is where the more, the real meat of it is. Because you have a couple different possibilities. You've made changes in a local timeline, and you are trying to push to a remote timeline, and that remote timeline may be the same as yours. It may have changes of its own. Yours may be more up to date than its. So there's a couple different basic just states that can happen. Let alone, you know, if we're getting changes while we're doing the synchronization. Fortunately for us, we already have what many CRDT things go for with, although it's more expressive but less parallel, um, so far as our DNA transforms. Okay, so that's what I was going back over here for. Okay, so here's our march. This is our context. It's the thing that we're thinking of as our timeline, even though each one of these things is the timeline. We can go in here to local repo change. We can make a change here. Okay. We've now just changed a timeline inside of our local change timeline just for fun. Navigation stack personality. Okay, but so this is our timeline that we're looking at. And the way that these are made, like I said, with a fork, 9C5BA, is this it? Yeah. So the first one is always going to be a fork because you're forking from some source. You're creating a timeline. You're creating a timeline if you have a unique thing. That's these, the timestamp and the UUID. But so these DNA, we're looking at this as these DNA are the transforms that are applied, and these are like our diffs. So there's the fork we already looked at. Here's a mutate. Let's look at this one. So we're going to go over here, duplicate. We're going to look at that mutate. And so here is where we did our initial, when we first made it, we added the text timestamp. I want to get to one of the mutations though that have, well, we can leave that up. So that mutated internal data. So whenever you change the internal data field, you do a mutate. When you do changing the relationships, you do a relate. And those are our three primary transforms: a fork, a mutate, intrinsic data, and a relate, extrinsic data. So we're going to look at that relate here. Relations to add, talking about the comments. Here's our initial comment. Remember that initial comment? Well, it's got a little slice of it there for some context. It's its own timeline. Okay, but the point is that this encapsulates the data of what we're doing, right? So we're transforming it via a relationship with this data. And so what we can do is, unlike event sourcing, where the event sourcing paradigm is meant to rehydrate an aggregate, we're able to apply transforms to timelines, much like how transforms, I don't remember the CRDT jargon, what it is, but CRDTs, to make them idempotent, also have this to where if it has a transform applied, then that's good enough. Now, order, if order is necessary, we're not to that point of ordering being necessary as far as synchronization goes. If it's order is necessary, then you should be working locally. And you're always going to have a locking mechanism. But for us, at the very least, just for synchronization, for our use case with a chat with relatively few number of things happening, we just want to think of a timeline as being equivalent if each of the transforms is applied. So in this case, we have this relate, and so we go to do the synchronization. Going back over here to the code. So whenever I say the TJPs, like in this, we're going to iterate through the TJP addresses. That means through the timelines. A temporal junction point, for anyone, if you already know, then congratulations. But it's from Back to the Future. So Back to the Future 2, they're coming out from the, they go to the future, and when they come back, it's all changed to Biff, the Biff timeline. And they come to realize that Biff went back into time to 1955 also. And Doc Brown says, what, 1955, it could be that has some significance for the space-time continuum, or it could just be a coincidence. But the space-time continuum, that's what we're talking about. It's a junction point that's in a timeline that's important. For us right now, we're just thinking of a birthday. So a birthday, it gives us a way of naming a timeline to where now when we want to go reference that timeline, if we just have if we try to reference just the individual points in time, that gets real iffy on trying to say, hey, do you have this point or this point? When really what you just want to know is, do you have this timeline? So TJP is it's like a way of saying the timeline address or the stream address. But anyway, what I want to get to here is this reconcile part. So this is a bunch of this stuff is important, but it's complicated. The main thing is that we want to go through those cases. Okay, the latest address in the store, if there's nothing in the store, then we're pushing a brand new timeline. So we'll go down here, else the timeline does not exist in the store. So reconcile by inserting the first time into the store, right? That's the easiest case. So the very first time that we published the chat, which I did before starting this video, but that's where the timeline does not exist yet. Another, once you're inside this branch where it is already in the store, okay, the store does have it. You need to find out, is the latest in the store and the latest in the address, are they equal? If so, then it's already synced up. There's nothing more to do for that timeline. Or if the local, only the local has changes, then you just need to update the synchronization space with your local changes. So here's the reconcile by updating the store. So we're taking our local changes. If we're using git, we do a git push to the remote, and the remote doesn't have any of those changes, and it doesn't have any changes elsewhere, so it just fast forwards its own branch, and that's what we're doing. We're fast forwarding the store, the synchronization space. And the part that becomes interesting for us, for the ibgib protocol in particular, is if the store has changes, and maybe also the local branch has changes, local timeline. So here, long comment for a log, a console log here. Storage changes, non-local, maybe also local has changes. So now we have to analyze our timelines and merge them appropriately. So that's where it gets interesting. If you're still with me, by the way, congratulations. That's pretty impressive. All right. So there's two cases. One, if the local has DNA, if we're dealing with the DNA scenario. If not, we're going to do what other timelines do, or what other technologies do, which is you try to just merge the state. And what happens is that you have just some deterministic way of merging two objects. In our case, I don't know, it's just like merging JavaScript objects. If it's an array and they have different objects, then it uses a default. If it doesn't have it in one, it does have it in the other, then it adds it, that sort of thing. That's not likely though in our particular use case for our most of our data on our local prototype. Most of it has DNA, as we've looked at. Again, these forks, the mutate, the relate, the fork, those are the DNA, those are the transforms, on graph transforms, cryptographically verifiable transforms, and also cryptographically enabling an audit trail for the transforms. So we have this, we reconcile local storage by the DNA, and here's again, I'm not going to go through all of the little stuff for you, but the main thing is that we're looking at the two timelines, and we're looking at the DNA, the transforms in the two timelines, and we're applying each one to the other, or keeping track of the results of those transforms, such that whatever our end product is, we will have all of the transforms applied. And I haven't said it explicitly, but in the relate, that's also an unrelate. And a mutate obviously can go in both directions of adding and removing data. So when you go to delete something, if it's a relationship, then it's the same thing. You're still applying some DNA. So much like the canonical ledger example with event sourcing, where you increment and decrement, or credit and debit. When you go to do the inverse of the transform, you add a credit. You can also add a debit to do an inverse for that transform. So that is what this is doing in the background on the server side, although all of this right now is happening locally because we have our long polling adapter. But this also could be executed remotely on a different node or a different space, a different node with a different space. And then what happens is, each time you do a timeline, you get updates locally, for the local space. And that's where this start sync, sorry for the scrolling here. Handle Saga updates. I think it's going to go to here. So each time something happens there, it's getting a Saga update. The start is the very beginning, inserted, updated, merged DNA, merged state, already synced, completed. Okay, that's what's happening when, is it still just spinning? Okay, that's what's happening right here. So all of those, that saga is executing when the little spinner is going. So it's just started off, and it's getting updates. Okay, okay, that timeline's the same. That timeline's different. Oh, that's unusual. There you go, prototype demo. Oh, there we go. Oh, I wonder, remember we did a local repo change inside of it? Ah, see, so it didn't. Oh, I'm not sure if we ever pushed it. And we left before the auto synchronization happened. So just for fun. But we'll just watch it in all its glory. There we go. We're not waiting for the polling to happen. There we go. There's our change there. Because that hadn't sent. Not sure how my stack got changed up, but all right. So now we've had a deep dive into why does our chat app look so crappy? And it's because it's me doing the entire stack. Also the conception of it. So this kind of thing, I've been working for IoT distributed computation before microservices happened. Oh, that was one thing I wanted to show. We'll end on this, a little piece of history. For my personal history, anyway. This, can we see it? There we go. This is my whiteboard from many, many years ago about autonomous services. So before microservices were a thing, I was looking at the architecture of having autonomous services work on a monotonically increasing data set. And then, that's when microservices started coming out, and, this was 15 years ago. But the problem was, how do you create the addressing? And that's what's taken so long. I mean, it's been, many, many little changes over the years, but yeah, how do you have a plugin architecture where the plugin architecture itself is pluggable? And how do you address that? Literally address it. So that's a little piece of history. Autonomous services. That's how this sort of thing, when you think of chatbots, you think of sharing spaces and also a decentralized identity mechanism, which we'll have to get into another time because I haven't implemented my keystone architecture here. But suffice to say that the identity mechanism is different than other approaches Well, we'll do one more thing. One more thing here. Tell you what. We'll look at okay. We'll look at what a did is from the lens of an ibgib address, okay? Because they're very similar. This was way before the did came around, but so here it is. Here is their identifier. They have some metadata, right? They have a schema. They have an identifier for a local identifier, and then they have the hash address, right? But all of this specification lives off-chain, and it's not simply a part of the protocol itself. Whereas with the ibgib stuff, this is metadata. You have a hash, so you could actually have the identifier, the lists of identifiers, here's the intrinsic data. This is like a relationship that has a pointer to another address. These are intrinsic data as primitives. Here's a named relationship, right? Intrinsic data, named relationship, intrinsic data. So at the very least, you can see that the ibgib stuff maps easily, or would map easily, to a did, but there are design decisions that somebody else is making for them. But for me, the ibgib layer, the very small layer of metadata, has just the right amount of flexibility combined with the cryptographic features that we like from blockchains. And what that will end up looking like is you can have ad hoc blockchain architectures, consensus algorithms, witnessing algorithms, to where they can, because both the data and the metadata live on the same graph, in the same graph, you can have a more biological, a more uniform approach to how these things can evolve over time, because we're focusing on what's more of what I call a semantic version control. And we'll end on that. Got to end somewhere, right? After, geez, an hour and 30 minutes. Okay, so if you made it this far, God bless you. I mean, you know, appreciate it. If you made it this far, you should be hitting me up for sure. In the comments, you could leave a comment or go to the websites. Is that what this one is? There we go. Oh, what was that? That was when just before leaving for my bike trip to Albuquerque. Okay, so you can go over here and hit me up on this, or right here. Issue tracker is probably the easiest one. Or email me or leave a comment. But especially if you're a front-end person or a business person that has access to front-end persons and other people like that. Yeah, basically I'm just looking to get this design, get this architecture out there that is an alternative for what people think of as blockchain approaches. So But that's for another video. Alright, thanks for watching.